Okay, decided to record later in the day than I normally would on a Tuesday so I can get this done. Alright, we're going to talk about how to find the center of mass of a triangle using a calculus-based method in single integrals. This can be done with double integrals, and if you want to learn how to do that, I'd be happy to go over it with you. Most of you probably don't know how to do double integration though, so we're going to show how to do it with single integrals, and the whole trick is splitting an object up into appropriate shapes. So we're going to take a look at that, hopefully right here. This is the problem we're doing. You've been asked to hang a sign from a single vertical string. The sign has a triangular shape as shown and a mass m. The bottom of the sign is to be parallel to the ground. At what distance from the left end of the sign should you attach the support string? Okay, so I'm going to recopy all of this, and we're going to talk about why you would put the string in this particular place. So it has a width a along this side, a width b along that side. We're putting our coordinate system over at the edge here. We have x and y. We're going to take a representative shape right here. What we're basically doing is chopping it up into lots of pieces going along. We're going to take one of those as a representative piece, and we'll call it dm. That piece dm is a specific distance from the edge, and it has a specific height y. Alright, why would we want to hang it right above the center of mass, and why would that make it hang parallel? Well, because when you hang an object, the center of mass will always rotate until it's directly below the hanging point. That'll make a straight line down towards the center of the Earth. So if you want something to hang nice and parallel, you need to find the center of mass and put your hanging point directly above the top of it. Alright, so looking at this shape, what we're always trying to do is take and find something like RCM, and that looks like integral of the r with respect to dm over the integral of dm. Or, if, as in this case, it is uniform, you can integrate the dm, it's just the mass of the thing, and you'd get something like this. Now, specifically in this case, we only care about xcm, so we're actually going to do a 1 over m integral of x dm. Well, we need to think about what that mass is. And dm, in this case, is going to be the area density times the area of the shape. I guess I'd better be careful and use the uppercase A in this case. What is the area of this shape? Well, it's the width by the height, and the width is dx. It's a small piece along x because we're chopping it up along x. So that means dA is equal to y dx. And sigma is just the mass over the area, which in this case is the mass over 1/2 the base times the height, or 2m over a times b. Okay, so things are going relatively well, but you notice that y depends on where we are in x. It's a much longer thing if we go out further to the end. It's a much shorter thing if we're closer in. So we need some way of relating those, and there are two different ways of thinking about it. There's the algebra-based way, which is kind of what I run home to, where this point is 0, 0, and this point is a, b. And then we can find the equation of the line. So we look at the rise, it goes up by b over a run of a, x, and then plus an intercept. And the intercept in this case is over here, and it's 0. We basically just get y is equal to b over a times x. The other way of thinking about it is geometrically. We have two similar triangles. One of those triangles is x by y, by a hypotenuse, and the other one is a and b. And you can take similar parts of similar triangles and make a ratio. So y over b is equal to x over a, or y is equal to b over a times x. So they give the same result. All of this brought together in a single step lets us find the center of mass. So x is equal to 1 over m, the integral of x times, we'll start with our density, 2m over ab. Then we need the y and the dx. Well, the y is b over a times x, and then we get our dx. All right, we do have some things that will cancel here. I'm going to do that first. We need limits. The limits need to be where the mass is present. So the mass is present from 0 in x until we reach a in x. So we'll integrate from 0 to a. All right, let's take the constants out in front. So we have a 2 over a squared we can bring out in front. Then it's an integral of x times x squared dx between 0 and a. And the last step, we do the integration. We get x cubed over 3 between our limits. So we get 2 over 3a squared times a cubed minus 0 is just equal to 2a cubed over 3a squared, or 2/3 a. That's actually a general result for pretty much any triangle. You need to be careful how you think about it. But it's a pretty general result for triangles that you'd get 2/3 from the vertex or 1/3 from the flat side. You're not allowed to use that generally on tests. I will be asking you to prove something by calculus. So if I say show by calculus, or just say show really, you're going to have to use calculus or some method like calculus to demonstrate that the center of mass is in fact where it is. All right, this way of thinking is actually useful for the homework problem where you're trying to find the center of mass of the pyramid. So you can do m times g times h cm to find the energy stored in lifting a bunch of blocks up to build the pyramid. So yeah, have a look at that. This should be a help and some guidance as you work on that homework problem. Depending on the school, I think it's problem 4 or problem 5 in the momentum homework. Okay, that's going to be it for this one. There's one more example of how to use calculus coming up.